Hello everyone, welcome to the stream. Today we will be reviewing the results of us designing a new Pmod for the icebreaker. The Pmod that we were working on the several previous streams, and on the last one we assembled is a device that allows us to connect retro console gamepads to the icebreaker so that we can connect controllers, and it has also audio on it. So this is how it looks. Let's see. So the desktop is here. So this is the Pmod, and let me just... So we designed it and we laid it out, and then I ordered the boards, and in the last stream we assembled these. So what it is a level shifter that allows us to drive gamepads that essentially contain a shift register inside and read them out. So it supports up to 4 controllers. This particular pod, so I decided that we should have pods for the game controllers so that we can have multiple different connectors. So for example, if you decide you want to extend it or connect something of your own, or you have some cheapo clone controllers that you don't want to keep using the connectors, you can cut them off and use them with this connector, or you can use the SNES connectors. And I already got the connectors themselves, but the pod is not designed yet. That is for NES. So what the abbreviations might not mean much for the younger people in the crowd here. So NES stands for Nintendo Entertainment System, or in Japan it was called Famicom. And this is one of the first widely popular game consoles that you could connect to your TV. Well, first definitely not, but it was one of the most popular ones from the Nintendo company. There were others before that, obviously. There was Pong and whatnot, so sorry, I don't want to represent history wrongly here, but this was very, very popular. So NES, and NES itself was, as far as I know, not super popular in Europe, but definitely as Super Nintendo Entertainment System, which came after that, was very popular. And I remember my friends from school having these consoles and we playing Mario Kart on this. So as I am at the age where that stuff becomes quite nostalgic, I wanted to work on this. Yes, so Tennis for Two, or Pong, was one of the very first video games that you could connect to the TV. I remember actually playing some of those games. A family friend that we visited once had a TV that you could switch to a mode that had the a shooter game where you had like a white square that you could shoot with like a light gun. And so Tennis for Two, that is even earlier, but that's on mainframe. That was way before it was at home, as far as I remember. Again, don't ask me for the exact history of these things. There are people that know it much more detailed than I do. But I think Tennis for Two was PDP mainframe, like maybe earlier, I don't know, but it's like I know that this was quite early on. There is a lot of disputes what was the first video game in general. There's some people that claim that Tennis for Two. There are some others that thought there is some other game that was there earlier, but as it comes to very popular and very widely sold in huge quantities game consoles, definitely NES is one of them. That was fairly early on and very widely popular. There are others that were before that, but not in those quantities. So SNES was, from how I remember my childhood, incredibly popular. A lot of my friends had those. My parents didn't want to buy a game console for me, but that's they wanted me to go to school. But yeah, the NES is very, very interesting console. So anyways, the interesting part for us is that on an FPGA, if you want to interface to a gamepad, using more modern interfaces like USB or Bluetooth becomes much more complicated. So you want something that is fairly easy to interface to a FPGA, and things that are easy is SPI, so serial parallel interface, or in this case, let me look it up how this works. Let me look it up really quick. This is a little bit slightly ad hoc. I should have prepared slightly better than this. But super breadboard controller? What? On DigiKey? Okay, I have to look at that. That's weird. Oh, there. Oh, Maker IO. Ah, interesting. Anyway, so this actually contains the necessary information. So what you find in the NES, so Nintendo Entertainment System controller, that has less buttons, you only have one shift register. Let me pull one out for you. You can visually connect one to the other. So this is Nintendo Entertainment System, so NES. So it has 1, 2, 3, 4, 5, 6, 7, 8 buttons. So you have A and B, start and select, and the D-pad. So that's all the buttons you have. That's why you only need an 8-bit shift register. So this would be just half of the circuit here. And the Super NES has a few buttons more. So it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So 12 buttons. That's why you have 2 shift registers, which would result in 16 buttons, theoretically, that it would support. But only the lower 12 bits are actually connected. So let's see how that looks like. Maybe can I zoom this in somehow? No, probably not. Can I open this in a new tab? Yeah. There we go. So essentially, you have. So this is the lower bits. Now that I look at this, these are the lower bits. And these are the higher bits, at least the way I designed the Verilog to read it out. But you essentially have a clock line. This is data out. It comes out here, and clock, and where's the latch? This is the latch. So essentially, you have bits, 8 bits here and 8 bits in the lower one, and you pulse this line so that the state of these pins here where the buttons are connected is being stored in internal registers inside in one big latch in. And then with the clock, you can shift the data 1 bit by bit out through the data outline. So you see here, these 4 pins here are just pulled up, so they are always 1, and the other bits are all pulled up but have a button that can pull it down to ground. So every button that presses on you press on will cause this bit to be low, so a 0 instead of a 1 when a button is pressed. So you shift out this 16 bits out of the controller. In theory, you could just shift out less than that, only 12 bits and ignore the upper 4 bits and then relatch and shift out. But in normal cases, you are shifting out the full 16 bits, so you can store it in two 8-bit registers on the console. The consoles are considered 8-bit era consoles, so the registers are in the CPU are 8-bit in general, but you can. There is some debate. People would be they have heated debates and discussions how the 8-bit consoles are actually not 8-bit. They are more like a hybrid between 16 and 8-bit, depending on the bus width. It really depends on where you draw the line. But under the umbrella of the term 8-bit consoles, these consoles, this is what people mean with them. But anyways, so people can have discussions about everything, really. All right, so now that we have slightly explained how this works, we can get to what I designed here. Let's see, gamepad and audio. So for the gamepads themselves, I have 3 level shifters. Level shifters is a different thing than a shift register. Shift register is this one data register, and with each clock you can shift out like a caterpillar the bits out of it. And these are changing a voltage of the pins that you are connected to. So the signal pins can be either 3.3 volts or 5 volts or 1.8 volts. There are several standards over the years. So for example, RS232 or serial, old type serial, was plus minus 12 volts for signaling. But then you have the slightly more modern standard is 5 volts, which would be these theoretically are designed for 5 volt signaling. But most of the cheap clone controllers, these are cheap clone controllers. I have one of the NES controllers that is original. And SNES, I want to still get the original ones. They are designed to run on 5 volts. And I heard that there might be some of the original controller ports have issues running on 3.3 volts. So these you can undervolt and run on 3.3 volts. So the supply is 3.3 volts and the signals, so the data signals, are also 3.3 volts and it works fine. But the older original ones can have issues with that, so you might want to crank it up to 5 volts. So that's why we have this shift registers, or lever shifters, sorry. Level shifters, and these convert 3.3 volts to 5 volts. Also, they act as buffers if we only run both sides on the 3.3 volt supply, which makes the signal stronger and the capture more accurate. So it's nice to have them in there. In theory, you can just take one of those gamepads if they are tolerant of 3.3 volts and directly wire them into the Pmod connector. So with no additional circuitry. So you can do that. I wanted to, if I'm making a board here, I wanted to do it as good as possible and as flexible as possible. So we have the level shifters and we have a jumper here, which is here. We can switch between the 3.3 volt to 5 volt on the target side. So this is the target side, how I would call it, and this is the source side. So this is where the FPGA is connected, and this is the side where the gamepads are connected to. And this is the connector where it goes out on the ribbon cable to the pods. Then, because if you look here, we want to be able to run a game console on the Icebreaker, so we need some video output, and logical video output for these days would be actually DVI, so digital video interface, but it happens to use an HDMI connector. So this is the interesting confusion here. I've seen several people be confused by the fact that these Pmods are called DVI interfaces, and they were looking, where's the HDMI one? So the relationship between HDMI and DVI is such that the video portion of the HDMI interface is the same protocol as DVI. But DVI does not have any audio capability as far as I know. So HDMI added that functionality. So in the protocol, you can add audio to it. The chip that we are using here, no, HDMI does not support analog. So DVI is, so yeah, that's a very good point. So the VESA, I think VESA, which standardized the analog video, so VGA, so Video Graphics Association, I think, VGA, which was completely an analog protocol. Well, so it was still clocked by the pixel clock, but then you had analog voltages that were defining the RGB colors that were displayed. Then the same consortium wanted to go digital, so they developed DVI, which was also a connector. So that's the whole confusion there. In the DVI connector, there was separate pins inside it that were for digital and separate pins for analog. So you could still have VGA inside a DVI connector, or have the DVI digital data go through it, which then was moved over into the HDMI connector, and they also added audio capability. So because the Icebreaker uses the ICE40 UP5K, it is not fast enough really to clock out, and it's all with many asterisks attached. But essentially, it is easier for us to use a transmitter chip that generates the differential signals for the DVI interface. And then we are using the HDMI connector because this is the most common connection that people have on their monitors, on their TVs and whatnot. So the interface that goes into the encoder chip is a parallel interface, which has, in this configuration, it has 12 bits, which are assigned 333 for RGB, and then it has vertical sync and horizontal sync. So it works almost as a VGA interface, so it is very easy to use for a FPGA developer beginner, and it is pretty easy to set up, and you don't need to copy someone else's blocks. You can develop it from scratch yourself. So you don't have to write your, if you want to learn and write everything from scratch yourself, which is a very good practice if you are learning things, then using these encoder chips is a pretty good approach for this. Yes, of course, we have example blocks and example cores that you can use, because I'm saying this in respect that some people were saying, oh, if you use the bigger FPGAs that can drive HDMI directly, this is so super easy because you can just use someone else's block. But if you wanted to implement the video and everything from scratch yourself for reasons of learning, then it is not as simple. It is harder from the perspective of a person learning the systems. So that's my argument for the encoder chips from the learning perspective, as well as from the perspective of using a smaller chip. It allows us to even drive 1080p video out of the ICE40 UP5K, which is pretty impressive. And I didn't think this was possible until Sylvain proved everyone wrong and implemented a core that can actually do 1080p on this, which is, yeah, it still blows my mind. So we want video, and in this case it is only 12-bit color resolution, which is still already pretty decent. We also made, or I mean, there is a version of this that is that you can. It unfortunately has to be rewired differently, but you can use the 12 bits here in two. Very good, Sylvain. We have to question your abilities more often then, I guess. Oh man, yeah, that's great. So this HDMI, there is a version that you can use DDR. So DDR means double data rate. So usually how you clock data into a device is on one of the flanks of the clock signal. So you either have on the rising edge or the falling edge, but you choose one and not both. Usually that's single-ended or just a single-ended signal. So you when the clock goes high, the device samples the data that you have in the data bus and you're good. With DDR, you are doing it on both edges, on the rising and falling edge. So what this chip also supports is 24-bit color DDR, meaning you, on the rising edge, you clock in the first 12 bits, and on this falling edge, you clock in the second half of the 12 bits, resulting in 24-bit color per pixel. So you clock it still with the same clock, but you send in twice as much data into the chip to get a full color resolution DVI video out of this part. So I assembled some prototype boards that are wired the necessary way to do this. Unfortunately, the way you have to wire it is different. So it has to be a separate PCB. You could bodge wire it, sure, if you have one of the 12-bit ones, but it is pretty complicated otherwise. But yeah, there's a lot of wiring you have to do. So these boards are, one of them is going to Sylvain actually. Let's see what he can do with that. But they will be available on 1bit² eventually, as well as the smaller version, which is a single Pmod. So this is a DVI only 4-bit color. So this means you have red, green, blue, and intensity. So essentially it is CGA color, where you can get red, green, blue, magenta, what is it, cyan, yellow, and then a brighter and dimmer version of the colors. So CGA essentially also had, for the dim yellow, it had brown, I think, which was a weird wiring in the video interface. I don't have that in this part, but it is very close to the CGA colors palette. Yeah, a dozen jumpers and it will be fine. Very well said, a little bit. So Holzfrau has a very good question here. While somewhat on topic, would you recommend starting with the open source toolchains for FPGA beginners? I have trouble with the installation of, say, PLL blocks and stuff like that. They just seem to appear out of nothing and don't find a lot of documentation so far. So first of all, join our Discord. I'm happy to walk you through it. There are others that can help you with that. Instantiating the PLLs is, especially on the ICE40, it's pretty simple. It's just a block of the text. You will see it actually later now. I will show you the code used for the clocking in data, and I'm using actually the PLL in there. So just hang on, you will see the PLL instantiation. So essentially, I do definitely recommend using the open source toolchain even as a beginner. The reason is the vendor tools like to hide blocks from you, and also I personally am more of a command line person myself, so I rather wait a second, is the audio clipping a lot by any chance in here? I just realized that it was getting into the red area. Let me know if you hear a lot of clipping by any chance. So just want to make sure that the audio is fine. Anyways, so yes, the open source tools are, the advantage is they will work on Windows, Linux, and Mac OS. The vendor tools usually work on Windows and maybe on Linux. You need a UI which is hiding a lot of functionality from you, and the open tools you can use in multiple ways. Also, the documentation of how to use the open tools, because the community is so vibrant, is growing very rapidly, and it can be applied to all the chips that are supported by the open source toolchain and not just vendor specific. So currently the open tools support mainly Lattice, so it is ICE40 and ECP5, but there are more vendors, FPGAs are being added to the mix. So, and also, right, that's a very good point. The open source tools are incredibly fast. So the synthesis time and your turnaround time of building something is much faster than using vendor tools. The vendor tools are optimized to create the fast. Actually, this is not 100% true. So in theory, you would say, oh, they are slower because they are trying to give you the best possible result and fastest design. But if you put them side by side, the open tools, at least for the ICE40, you get pretty much equivalent results. There are some corner cases where things are a little bit faster with the vendor tools, but in general, the results are equivalent, and the open source tools are faster in synthesizing stuff. So you, as a person that is learning, you don't want to, every time you make a mistake and fix something, wait for 5 minutes, right? So yeah, again, open tools. Yes, they are definitely production ready. There are products that are being sold that are completely synthesized with the open source tools. This is growing, and there are more and more companies starting their startups based on open source tools. So it's they are definitely, ICE40 is completely ready. ECP5 to a big degree, with I think CERDES is not 100%. So it is supported, but I think the parameter generation, there's not a tool for generating the parameters for the CERDES. So you have to use the vendor tools to generate the configuration for the CERDES block, but you can then put it into the open source tools and keep using it. At least that's how I understand how it works. But these things will be coming, and then yeah, this I'm seeing, like, really it's doing weird stuff here. Maybe I'm getting some interference on my receiver. That is possible. Katzfather, thank you for following. Jiggly girls, hello. Anyways, let's go back to this. So I'm happy to answer your basic question. Today is more completely a show and tell stream, and I'm happy to answer any questions you have about FPGA and open source stuff while we are at it. So the second part to this design Yeah. So the second part to the Pmod is getting audio. So this is the second audio. The second part is audio, and because we only had 2 pins left on the Pmod, and yeah, what I was getting to essentially is we want to use the HDMI, so we want to use the third Pmod connector to essentially add the gamepad interface and get also audio out of the board. So as I said, we only use the DVI encoder and not an HDMI encoder, and the reasons are pretty much legal reasons. Because of HDCP, so the problems with because of the yeah, so ULX is very nice board. It's a very cool board, but as a beginner, I would honestly start with smaller things. I would actually, yeah, I might be biased with the Icebreaker, but I think starting with a smaller FPGA is a very good starting point, where you actually are forced to make your designs, or the tiny FPGA BX, yes, totally. But being forced to actually make good designs that actually fit, and not starting with a big FPGA like the one on ULX, is giving you a better learning opportunity, in my opinion. Also, the synthesis will be even shorter than on the ULX because it's a smaller FPGA. So I think the Icebreaker is a better starting point, and then you can graduate to the ULX and start doing more complex stuff. The problem I see with beginners going to a huge board with a huge FPGA like the ULX is that yeah, so iStick is also an option with the yeah, the iStick is a good board, but it has its own issues. That's why we designed the Icebreaker. It was from the lessons we learned from the iStick. The iStick is nice because it's just $25, but the problem is the reason why it's $25 because Lattice basically gives them out almost for free. They don't have any, like, at least FPGA costs on there. So with the Icebreaker, we want to finance also my development and adding more features, adding more Pmods, adding more documentation, adding more workshops. There's a workshop for the Icebreaker that I did on at CCC that you can run through and learn stuff. No, I will not make the Icebreaker more cheaper because that's not the reason for Icebreaker to be the way it is that people like me can dedicate like full-time work into this. And I know that students might find it difficult to justify. But if you want a learning device that you actually want to learn from, I recommend that you find someone nice to get that board to you. But oh, Glasgow is not an FPGA development board. So that's the difference. So Glasgow is a very nice board as a tool. It's a very good tool for certain applications, like doing the applets to interface to devices and interface to protocols. But it is on the side of a tool and not on as a learning platform. It's the Icebreaker is designed to be a learning platform. That's why we what our priority was to have the Pmod interfaces, which are a standard, so you can get a lot of different peripherals depending on what you want to work on. as well as make it so that all the pins or the I/O is accessible. So after you're done learning, you can use it as a development board, and we are not stealing GPIO from you that you can use for your own hardware that you are developing. So the core idea of the Icebreaker is be a teaching and a workshop specific board first, and after you're done with it, be moddable and modifiable and hackable, so that you can develop your own ideas and keep going until your designs outgrow that size of an FPGA. And still, after quite a while developing a lot of stuff myself and with the community, there's so many things that we are still no one even attempted to do on this. There's a lot to still do and interesting stuff to learn and develop for the tiny ICE40 up 5K. So that said, again, I love the ULX. It's a great board, especially if you want to have all the different retro computers on it. You can have that. But I feel this is like one step beyond the ICE40. Especially if you are trying to learn to develop embedded or digital designs. So that's also a good question. Verilog and Migen. That really depends. It's a hard question to answer. I think it is always good to learn some Verilog. Even though it has its drawbacks, because the Verilog but by now the open tools support VHDL with a plugin called GHDL, but I don't see this. So first of all, there's a much smaller industry that is using it. It's only popular in Europe, and it's some military related stuff here in the US. With Verilog, you have a much broader, it's like if you are looking at this from not just hobby perspective, but you want to get a job in this. And so Verilog is a much better language. It gives you much broader opportunities later if you learn Verilog. Second of all, Verilog is as horrible as VHDL, if you ask me. They both suck. They are both terrible languages. VHDL is incredibly verbose, incredibly a lot of boilerplate, but it is... Yes, U.S. military is an example. It's like, yeah, but that has to mean you want to work for the U.S. military. Anyways, I think learning some Verilog is a good idea, especially there's a lot of resources. There is a lot of existing designs for Verilog. VHDL is fine if you're at a German university or something, but it wouldn't be my first choice. I learned VHDL first, and I don't feel either way. Both of them suck, in my opinion. Migen is a much better improvement in again, in my opinion, Migen is much better, but after... No, System Verilog, again, it is adding some new features, but it's again a consortium design thing. System Verilog makes some things easier, but yeah, it's still just drop in a bucket. Migen is much better designed. It learns a lot of lessons. Never saw a company asking for FPGA designer who know Verilog. Yeah, it's Europe. It's a European language, but the problem is this is what is being taught in schools, and I did learn VHDL also in school at the university. Oh, my hard disk is running low. Sorry. I'm doing a recording the video. Let me just really quick delete old streams. Just give me a second here. Let's not delete my stream recording from today. That's the important part. Yeah, I forgot to delete previous stream recordings from the machine that I moved away. Is it now gone? Yeah, so that should do it. All right. Alrighty. Anyways, so I don't really so let's get back to the NMigen thing. Why I think NMigen is great. So it learns a lot of lessons from Verilog and VHDL and other HDL languages, and NMigen also learns lessons from Migen, which was its predecessor. So it already brings you a few steps further. And second of all, it is hosted within Python. So the important thing is, like, some people say it's like, oh, I hate Python, so I will not use it. It's like, but NMigen is essentially happens to be written within Python, and it is not trying to be a DSL, so the domain-specific language. It is, or it is actually a DSL in a sense. So basically, it is designed to be specific for hardware design, but it is hosted within Python. And so if you don't want to write much Python, you don't have to implement it in NMigen. The advantage of being hosted within Python is you have access to all the packages that Python provides. If you want to use them, you can expand on that, and you can automate a lot of things. So if you look at projects like Litex that are just gluing together a lot of functionality, including Verilog designs and including Scala, not Scala, it's what is the a lot of different languages that you can pull in. And so it is chiseled. Thank you. That's what it is. Yeah. So if you have, it can pull it all in, and it can automate everything, because you can use Python to automate things that are not essentially NMigen, and then NMigen is just part of it, and it can adapt and be scripted from the Python side of things. So it is becoming an incredibly powerful tool that is sourcing from the whole universe of Python, and can automate your creation of your SoC, so systems on chips, which contain your CPU core and whatnot. So NMigen, in my opinion, is the way forward. This is where a lot of the community is going, and it is getting a lot of support from a bunch of very smart people that are working on this stuff. So that's why I say it is difficult for me to say which one you should start with, because the concepts you learning VHDL or Verilog, doesn't matter, will apply also to NMigen. The basic design of digital design in general has specific concepts that are independent of the language. Doesn't matter. You have to learn them. They are very different from software development. This is the hard step. It's not the language is the hard step, in my opinion, at all. The language doesn't matter. What matters is thinking in digital design. That's the hard part. And choose the poison yourself. Doesn't matter. What you will have to learn is, how do I think about clock cycles, synchronization, clock domains? How do I design state machines? how do I simulate, how do I read traces, how do I debug this kind of stuff. At the end, this is the hard part. Just like as my computer science teachers always were saying, it's like, you are not here to learn how to program. You are here to learn how to solve problems. And that's the core idea you should take away from here, is learning how to design, how to solve problems from the digital design perspective. That's what you have to learn. And what language you will at the end use, that doesn't matter. You will still have to keep learning new languages later on. It's not like you can rest on your laurels and spend the rest of the 50 or 40 years of your career and just use your one tool you learned in school. There are people like that, but it's pretty boring that way. And you really limit your opportunities down the road. Yeah. Yes, sketching stuff out in a notebook is really useful. Yes, that's a very good idea. So this is I saw a person at CCC that is working on integrating NMygen and a Wavedrum into the Python notebook. And so not just the physical paper notebook, which is also agreed this is a very good idea. I did that actually for my designs, but also being able to do it in the Python notebooks and essentially simulate and change your designs within a Python notebook. It's really, really cool, especially for teaching. I think that will be a game changer, where you can actually, yeah, Wavedrum is great. We might look at that. Anyways, so what's next? Now that we talked about the hardware, I wanted to show you the hardware that, or the gateware that I designed. So as I said, you have. So I wanted to. So I made 3 of these boards, and I had to send them out to developers. So I sent one to Sylvain and one to Hedge, and they are working on implementing something really exciting. They are working on implementing a SoC dedicated to running ScumVM on the Icebreaker. So that is very exciting. I'm really looking forward to that. And they wanted some controllers, so they were going to them so that they can keep working on that project. So you will be able to essentially play point-and-click adventure games using the gamepads and getting the audio out of the Pmod on your Icebreaker. So that is very exciting, because we already have a port of NES and Game Boy that have certain level. Yeah, Monkey Island time, yay! So yeah. Anyways, so the next thing I wanted to talk about is the HDL design that I did to test out that the gamepads are working. So that was the first thing I wanted to test. So what I did is, let me... So I took my notebook and I drew the following thing. So this was basically a sketch on top of here. So these were just my rough thoughts that I had. So gamepad shift register, and then I was thinking about how the signal comes together. So we have the latch, and then we have a clock and the bits coming out. And on the very bottom, you see in pencil, these are the state machine states. And so you see idle and latch and then read and clock and read and clock. So it repeats many times until it gets to the last clock on the very right side and then goes to idle on the bottom. So I'm not these things here. So this and this. So this was my basically a sketch to give myself a mental crutch how the states of the state machine have to come together. So the big difference between software writing, well, you do state machines also in software, but in FPGA, because everything is essentially happening at the same time, you have to force the thing to actually create a sequence. So what you do is, let's open the HDL design. That would be it. So what I started with is just a module, and this module has several input parameters, which we will get back to in a second. But the most important thing is actually this. So we have 4 states that the machine is taking. It is idle, which would be 0. It is in latch, so it is doing the latching of the shift register. Then it reads the data and then clocks it. So there's a little bit of an overlap because the data also is changing the clock output. But that's how I was thinking about it. The most important thing that I also did is, if you think about this, I approach it. This might be not the right way of doing it, but how I think about states of the state machine is, when I'm in idle, I check so this is the state machine state idle, this section here. And if I'm in idle, I then prepare the next step and switch to it. So that's how I do it. It's like, I'm in idle, so I set everything to be correct for the next state and switch to that state. So in this case, latch has to go high and clock register still stays as 0, and then I go into the latch state. And then I'm in latch state and I prepare it for the data state, which would be setting latch to 0, setting clock to 0 still, reading in, resetting the registers, the data registers, and then saying that data ready is not ready, and switching to the GPS state data. So all these things happen at the same time. So basically it says, at the end of this clock cycle, where I'm in here, please make sure that all these things are true. So that's how you think about this. You don't think about them in a sequence when you were programming, where you do this one thing, this would be the second thing, third thing, fourth thing. All these things are true at the end of the cycle. And then we are in data state, so we read in a bit from the data bits. So we have 4 gamepads connected, so we read in the 4 gamepad states into the shift register and shift the data. You see, we have this bit. This is the highest significant bit of, so this is how you array stuff together. You take the old register, the bits 15 to 1, so the 0 bit is being thrown away, and we add the data on top of it. So if you think about this, the first bit we are pulling in will go in the least significant bit and then slowly move into the register so that it eventually ends up to be bit 1 after we shifted 16 bits. And then we say clock register high, so meaning we read in the data and we set the clock pin high at the end of the cycle. And so we go into the clock and we say, okay, at the end of the cycle, the clock pin will go low, and we can check if we should branch what this next state should be. So we check if we already shifted in all the data in and we are done, so we can go into idle state again. or we still have bits to read in, so we still go into the data state and cycle through these two states on and on and on and on until we read in 16 bits. So that explained, this is the state machine. That's the core of the magic here. The other interesting side note to this is what you do is actually create a strobe instead of we create a strobe. So basically we make sure that let's see, let me think. Oh, right. So we don't want to read in the bits from the gamepads at the full clock speed that our system is running at. Our system is running at, I think, 42 megahertz, if I'm not mistaken. Yeah, so this is the PLL block that I was, so Holzfrau, if you look at this, this is the PLL instantiation here. It essentially takes clock in and spits out 42 megahertz clock using these parameters as its settings to get the PLL configured correctly. There is an ICE PLL tool that can generate these parameters. And you can get those yeah, they seem magic, but they're not. But they're, any complex enough technology is indistinguishable from magic, right? So yeah, we run at 42 megahertz. These shift registers, they can't handle such high speeds. So what we have to do is divide it down. And the one main thing that I learned when I learned HDL design in school was not VHDL, because I don't remember any of it. But what I remember is clock everything from the main clock. Never generate with your fabric clocks that you are triggering on. So that's a very important thing. So I could essentially say, I take the external clock, use a counter to divide it down, and generate a signal that is a slower clock, and then have an always pos edge new clock, the generated clock, down here, which is a slower one. And this was something my professor said. It's like, no, don't do that, because you're creating delays and everything, and causing a lot of timing issues. If you do that, what you want to do is clock your thing here at the full clock speed, but have a signal that you're checking at the edge of that high-speed signal if this is time to do your thing. So we create a strobe clock that is only going high for one clock cycle of the main high-speed cycle clock. I will show you in a simulation in a minute. And that will cause this to be clocked slower, but still happen within one clock cycle of the high-speed clock. So this is what we do here. We have this clock, and it takes divides down and then generates a blip, a small blip, every so many cycles to create a slower signal. Yeah, so this is part of Ice Storm. So if you install a toolchain, so just let me show you the PLL thing. So this is, in this case, I installed it as part of the Summon FPGA tools. So depending on which binary install you're using. So this is a compiled one, and this has Ice PLL. So if I run Ice PLL, you will get this. So these are the defaults. Given is 12 megahertz, output is 60 megahertz, and then it gives you the divvar, divf, and divq parameters, as well as filter range. That's the tool is part of the open source tools. All right, so let's go back. So we have that blip, And now, after I started working on this, of course, I made mistakes. So I was like, oh, now I have to think about this. But remember, simulate first, then go to the hardware. Simulate, simulate, simulate. So what I did, I created a target, or I created a test bench. That's how they are called. So this is the test bench. And this is a special Verilog file that instantiates my gamepad with the interface to it. So the interface is, so the parameter is here, the divider. So in this case, it is 0, but we will play with that, increase this. And then, we are running at full speed clock. So here we have every 5 nanoseconds. So I think that's the time scale is 1 nanosecond in here. And then we do always at 5 nanoseconds clock invert. So it is essentially a clock of 10 nanosecond per period. But the timing in here, the time that we are using, the time base we are using here is not that important. The important, for me at least, not at this time. The important part for here is the functionality working right? So I usually just take 1 nanosecond time base, and then you create your design. And then the initial begin essentially sets at what time you want the reset to go low, because the reset is 1 first, then after 31 nanoseconds it goes low, and the whole simulation finishes after 20,000 nanoseconds. And every 5 nanoseconds we invert the clock. So that's the input to our machine, and then we instantiate our block, and then we can create a trace using simulation. So let's do that. I should go into the correct project. Icebreaker, examples. This is in the repository, so by the way. Gamepad, so you can find all this stuff here. Icebreaker examples, and the gamepad would be here. So this is the gamepad. And there's a README, hopefully describing all the details how to use it, including testing, how you can test it. So what we will do is create the VCD file. VCD is a trace file of the execution. So let's do. I should learn how to cut and paste correctly. Anyway, so this runs. That's simulation already run. So now we can display it. That's how fast simulation is. That's really lovely that it is so fast. And GTK wave, we start this. So this is GTK wave. And we see here on the left, there is a gamepad TB. I'm sorry, it is very small, but I should have changed the font here. But this is, I will read it out for you. So this is device under test instance. Yeah, I think I can. So this is just the icebreaker examples. This is the main icebreaker repository. So here you go. Okay, cool. I'm sorry. I will try to fix that for future streams when we are doing this kind of stuff. So the device under test contains, so we have the test bench itself. It has a few signals here on the left. And these are just the input signals into the test device. And device under test is here, and we take clock, and that's our high-speed clock. It doesn't seem like it, but it is. If we scroll out, zoom out, zoom out, zoom out, zoom out, 5 nanoseconds. So you see, this is the clock. Every 5 nanoseconds it inverts, as I said. So that's the input clock. And then we have a clock divider, and this one is not really dividing at the moment because we set the divider to 0. So it is actually not dividing at all, and it's just passing the signal through. And then we want the strobe, and we will see the strobe is also not doing anything. So we first of all, we want to see that the strobe is doing something. So I will go in here and send it to background. And now I can edit this file. And let's say we want to divide it by 4. So that would be 3, I think. No, I think it is 4 actually. So every 4, so this will create a strobe every 4 cycles of the main clock, dividing it by 4, right? So we will have a 1/4 speed clock. And now we can just build this. I don't need to reload this because I can press Ctrl-Shift-Reload, and then it reloads. And we see it now does this strobe 1, 2, 3, 4, 5. Oh, every 5. I'm sorry. So it is actually -1. I'm sorry. So yeah. So it would be here. That would be a divide by 4. So it is -1. So if we do this, so this is why you do simulation, because then you actually see what is happening. you do your thing. It's like, oh, I think this means that we were doing this thing. Oh, actually not. Imagine this doing it on hardware. You would have to like bring out onto one of the GPIO pins the clock so you can debug it, and you would have to do it with every single part of the system. And especially if you are further down the road, if something breaks earlier. And yeah, so if you, now we have this one clock cycle. So let's see, let's count them. First clock cycle, 2, 3, 4, 1, 2, 3, 4, 1. Yeah, there you go. So every 4th, just like in music, we have a 4/4 meter, right, or something. I'm terrible. I don't know music. Sorry. So yeah. Anyway, so we have that trigger, and now what we can look at is I don't care about reset really. Reset is also an interesting topic, but let's just keep going into the state. So state is this one. So we see states are being advanced here. So I can also change it to be data format, decimal, state 1, 2, 3, 2, 3, 2, 3. So if you remember, we named this, so this is the advantage of using NMigen. NMigen uses a very like nasty trick, but it's really ingenious to actually name the state. So you, in the trace, if you use an NMigen, you would see what state name it actually is. In this case, it is not named. You have to look up what the numbers mean in Verilog. So unless you do some look, I don't know, there might be some mechanism to do that in Verilog, but in NMigen it does it automatically from the get-go. So let's go back here, and we see that we have a state 1, 2, 3, 4. So 0 is idle, 1 is latch, data, clock. So we will see state 0 is idle, 1 is latch, 2 is data and clock, data, clock, data, clock, data, clock. A nice way also to visualize it so that you can see it better is actually switch this to analog. So you get the steps. And the important thing is to maybe add a little bit more vertical space to it. The problem with that is if you don't do anything, if you scroll, I'm scrolling to the right. So I'm going right in time. So it eventually will resize and make it full height, even though we have a state here. So what I have to do here is data format, analog, resizing, all data. Then it will stay up. See? So now it is 0, 1, 2, 3, 2, 3, 2, 3. So you see that it is on the top. Oh, it plopped. So it went to idle state again. So everything is good. Yeah, the analog thing is very confusing. Yeah. So now that we have the states, now let's look at the output signals. So one output signal we want to look at is latch. So GP latch. So you see, we go from idle to latch state, and the latch goes up and then low before it goes into the data state. And now we can also see what is the gamepad data. I think that's the register. So let's look at D1, D0. So that's input data. It's always high, doesn't matter. And D1 would be always low. So I didn't go through the pains of actually toggling these to generate proper data. But that should illustrate it well enough. And so we have the GP1 register, which would be corresponding with the 0 here. So 1 is 0. So gamepad data 0 goes into gamepad register 1. Yeah, don't ask. The reason is that the players are called 1, 2, 3, 4, not 0, 1, 2, 3. And I wanted this to correspond to the player port instead of the data line that it is named on the schematic. It's a bit inconsistent, I'm sorry. But if you look at where things are coming from, it becomes pretty clear. So, and the same thing with GP2. So we have those. Let's align them together. So we have always data coming in, which would be 0. And then, so you will be getting ones. Now, another thing we can do is change the data format to binary, and then we will see the content of the register. What we see here is during reset, we are resetting the registers to 0. They are undefined before this. So this is what the X's mean in... so this is an undefined state. So the strobe is undefined before this time. And then we latch and we start clocking in data. So, we want to see the clock of the gamepad clock. So that should be also here. There we go. So we have latch and the gamepad clock, and it goes high, low, high, low, high, low, switching between those two states. This is what is generating the clock. You don't really have to do that. In theory, you can do other things. You can use DDR of the GPIO also. It's like there are a lot of different tricks you can play how you generate clocks. And let's not get into that. I don't think that's... Yeah, so these signals, this is 15 lines that are 16 lines that are combined together. It can be a register or a wire. It doesn't matter. It will show it as one unit. I think I can break it down. Insert, there was an... there is a way of showing also the single signals somewhere. Gray filters, range fill. There is a way of showing... I think it might be here. Recurse import? I know there is a way of inserting just the split apart signals. So to unfold it. But I'm not finding it right now. Anyways, doesn't matter. What we are caring about is that we are shifting in the first bit. Yeah, it doesn't work the way I thought it was working. I could not get the enum thing to work. I might need to read some documentation on GTK Wave. So anyways, we clock in the first bit, which is 1 here and 0 here. So this one will stay always 0. the lower one, because we are only clocking in zeros. And here we see the 1 bit to populate in. So 1, and then it is shifting in the ones. 1, 1, 1. We see more and more ones being shifted in. And then, after this is filled in with ones, we are getting back to the idle state. And another thing that is important, after all these bits are shifted in, we have to let know the environment, like the other blocks, that we are done. So data ready is the signal that says that the data is finished. So you see, after this is all shifted in, the data ready bit goes high, that it is ready, before the next cycle of shifting in data starts, where it resets again to 0. So you have this time to read out these registers from that module. So this module has those registers, and the registers are valid for the outside world during the data ready bit being high. So you tell it, the outside world, it's like, look, I have finished data, now they are stable, you can read them if you at your now. And when it goes low, it's like, okay, don't touch it because it's probably invalid data. So so we are resetting it to 0 again, and then shifting it again for the next cycle, and again and then again and again. So this is what helped me to figure out how to get it right. I was off by 1 so many times in here, but being able to, as you saw, edit this. And for example, I want to go back to compressed display. So I want to remove the divider, let's say. So I go to the divider, set it to 0. I set div to 0, and then build it, go to GTK wave, reload, and it's done. So that's how quick the turnaround is if you are testing a module. It's really, really quick to just test, simulate, change things, just repeat, 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 repeat. And it is faster than doing it on the hardware. Because on the hardware, if we just build this, just building the design that I have, it still takes a little bit. It is taking a little bit longer than the simulation. A little bit longer, and I still have to flash it on the icebreaker. So simulation is a really good way of getting a feeling of what your design is supposed to do. Yeah, place and route takes a while. Sorry, my throat is getting dry. Should have a drink. It's a lot of talking. All right, so the next step is after we simulated this, we debugged this, we let's do this. Yeah, the programming also takes a little bit. You can speed up the programming. So if you look on the icebreaker on the back of the board, there is this jumper cluster. I'm not sure this is visible. But the jumper cluster, you can switch between the FTDI programming the flash chip, which is slower, or configuring directly the FPGA over SPI. You can do that. The iceprog minus big S will actually load the data directly into the FPGA instead of flashing it to the flash chip and then starting the chip. It's faster, but when you unpower it, it will lose its configuration, obviously, because the FPGA essentially behaves like a RAM chip. It's like a volatile memory. So it needs the FPGA. Oh, it's funny. I'm actually triggering the gamepads, so I'm displaying the buttons that are being pressed, so I can press with my fingers. It's like it's complete, no pull downs or pull ups, so I can just create random noise data on the gamepad. Anyways, I find it very funny. All right, so now after we debug this in simulation, we can go and have our design, which contains the PLL, which generates 42 megahertz clock. That clock is then fed into the gamepad here, so clock 24 megahertz, and the reset we have here, we generate the reset for this, and we take out the data out of the gamepad into these wires. So these are internal registers to the gamepad. There are different ways of doing it. We could, but there are internal registers that only have the stored in data. And then we have these wires that we connect to this module. And these wires then are later connected to this block, which takes the 42 megahertz clock, and when the GP data ready strobe is ready, copies the content of these wires into its own registers, and those in turn are connected to the LEDs. So of course I'm not displaying all the buttons, but these register the first 7 bits here, 7 bits, are connected to the LEDs. So this will be button 0, 1, 2, 3, 4, 5, and 6. What? 1, 2, 3, 4, 5, 6, 7. I should learn counting. But yeah, so 7 buttons, but starting with 0, it would be up to 6. Yes, that's correct. Confusing myself. Anyways, so this is one block that I do, and numbers are hard. Yes, sorry about that. And the second thing I do, I created a second, I instantiated another block that implements a UART output. And this one has a data register and a start bit. So you set this register and strobe this start bit, and then it will start sending it out and indicate that it is sending data and is busy on the busy bit. So this is an output, this is an input, and this is an input. And this is the connection to the pad that is the serial interface. So because we have the FTDI chip on here, serial is connected to the gamepad. And then, as the last thing, I have a special module that includes a state machine that is printing out the state of the buttons in over serial. So that one is a more complicated state machine with more states, which sends out the serial data. So it starts with idle, has a, and yeah, again, in my notebook, I went through here. How did I do this? GP serial. It's very cryptic though. I think I did some, this is how it looks. It's just a table of bits. And I was thinking about what states I have as numbers here. So yeah, 3, 2, 1, 0. So I think the columns were which nibble it is, because you have to send it out as nibbles. You want hex numbers, right? So hex number means for each 4 bits you have a nibble. And so the nibbles have a lookup table, which is the AHEX conversion. So you take 4 bits in lookup table and output a character. So for 0, you have 0. For 1, you have 1, 2, 3, 4, 5, and so on until you have F. So that's my lookup table. And then I have a second data block, which contains an escape sequence to move the cursor back up. I will show you in a second how it works, in how it manifests itself. But essentially, I'm printing 4 lines for the gamepads and then moving the cursor up in the terminal, and then up and up and up and up. So let's hook it up and show you how this actually works after you get through all these states and send out all this data with the more complicated state machine. So I have it currently designed so that, let's do desktop. So I have the icebreaker, and currently this design is using the Pmod 1 over here, and then we have the gamepad pod. Let's take a gamepad, which is here, gamepad, and we will plug it in. the right way around. So that's the gamepad plugged in. And now, first of all, we should see, without even getting the serial terminal running, if I press buttons, let's see if I can show you. So you should see on the head the LEDs go out. So that's button 1, that's button 2, then button 3, 4, and then 5 I think is up. And then we have these two guys, which are inverted. So these are inverted LEDs, so they will go on for the button press. Button press, and this one, yeah. So left is green, down is red. So this part seems to be working, so that's cool. So yeah, that was very excited when it worked for the first time. I was very happy. And now let's go into the serial terminal and let's go to desktop. So Minicom is the my poison of choice. So serial port setup. We need 115,200 as baud rate, and exit. Yeah, so clear. So that's how it looks. So this is printing. You see the cursor jumping around like crazy because I didn't disable it. But essentially, when you see I will press the buttons now on this, the characters are changing. Yeah, it's all just in hardware, no CPU running, just state machines doing serial out. And now if this is the second pad, so the shoulder buttons are on this nibble. So you have these 2 bits and nibble, nibble. And then we have the gamepad on the second, and the upper 4 bits stay high always. So the interesting thing is when the gamepad is not connected, because I added into my, I have to show you under the microscope really quick. So what I added is on all my data lines. Let's see. Can I focus? Focus. I added pull-up resistors or pull-down resistors. So I soldered in pull-down resistors. They were missing in the design. In the next revision of the board, I should add those. So they basically force the data lines of the gamepads to be low if nothing is connected. So I soldered in pull-down resistors. It was very convenient because ground pins on this connector are just next to the data pins. And I could encode, well, that would be, if I wanted to encode the number of the pad, I would have to do it in the gamepad, but it's not. Safrini, thank you for the bits. Sferini, awesome, thank you so much, I really appreciate it. So now you see if because I don't have pull down resistors or pull up resistors, I can poke it and it will just go nutters. Like with my finger, just scraping on this, it's like zeros and Fs. So yeah, now I will plug this back in. And this back in. And the cool thing is, because they are Fs or zeros, these are 0402 resistors, yeah, 0402. And you plug it into the first game port, and then the second game port. And always when there is a plugged-in game controller, this particular register goes high. So that's the nice part. So you can detect if there is a gamepad connected to the port by seeing if all the bits are 0 or all the bits are F. And I did mention that in the chat on Discord, and I think someone confirmed that uppermost 4 bits are being used to detect if a gamepad is connected or not in the actual game console itself. So that's interesting. So yeah, this way we can have gamepads, and that would be that part. I will take a very short break, and we will get to the audio part of this. Yeah, and I want to show you something very exciting as the very last thing. We don't have very much time left, but I will still try to show you everything. So the audio part is the next thing we should test. And the very last part, I want to show you something very exciting that I already posted on Twitter. You might already know what it is, but we should try to at least show it on stream in real life, that it is not fake, and see if it works. Like demo time. So let's see. Anyways, I will be right back. Just give me a second, and don't go away. Okay, sorry about that. I'm already back. Forbidden Acid, thank you for the follow. There was a bunch of people following, and I'm sorry I didn't give you all a shout out. I will look in a second. A bunch of new followers. That is wonderful. So let's look who we have here. Yeah, I think that's where I dropped off after you subscribing with Prime. Thank you so much. Then thank you for the follow for Freeman7, Decla Prus, Iking0, Theophar Karen, yes, Theophar Karen, Tio. Fred Marshall, thank you so much for the follow. Grazfather, thank you for the follow. Correlation Zone, thank you for the follow. Lil Washu, thank you for the follow. Chance of Bowd, that's apropos. Bod, right? Chance of Bod. How many Bod are you? Thank you for the follow. Sverini, thank you for the 10 bits. That's wonderful. And Jamartin's CD, Dens, Nesd, T-Nesd. Sorry, I'm butchering your name. Thank you for the follow. And Forbidden Masood, thank you for the follow. Thank you so much. Thank you all, and welcome to the stream. I hope you have some fun here. All right, so the next thing we wanted to look into was the audio output. So this is the part that I'm less confident about, because I am I'm a very much of an audio noob. I'm not doing a lot of audio design or audio circuitry design. So one thing we can do still before we fully move on from the gamepads is connect. I have this thing. So there's this very useful Pmod which breaks out the pins on separate pins. So we can hook that up between the gamepad. So this is something I also did, is hook this up. You can either use the logic analyzer, like the Bitmagic that we make. So Bitmagic you could connect here, but we can also connect the oscilloscope. I'm stuck. Oscilloscope. I need one probe and two probe. What did I drop? There we go. There we go. So now we can hook this up and actually look at the signals. Hopefully, there. I will have to move the oscilloscope a little bit. What happened here? Oh, yeah. There we go. I need some better capture device for the oscilloscope. So yeah, if we hook this up, let me quickly do that. Let's try. So this is ground. And then we have clock is this one. So you see there is a clock there. But I think we are not triggering on it. We will trigger on the latch. This should be latch. Yes. Oh, maybe I'm wrong. That's fine. Let's expand this. And then trigger menu, channel 3. Channel 3, and then level up. There we go. Now it's stable. So yeah. So this is latch, and now let's look at data. So I need one more probe. That's why you want an oscilloscope with 4 channels, not 2. Otherwise you need a logic analyzer already. Now what happened? Did this... Okay, let's see. I think I have an idea what that could be. There we go. Yes, it is. Aren't they all? The tabs are broken always. Yeah, I have to replace that Ethernet cable with one that has a working tab, so that this doesn't happen ever again. So anyways, let's get back to it. Sorry about that. It was eventful here. So anyways, this now we have the I'm not sure where it stopped running, but essentially we have the clock and the latch running, and now we can also look at the data. So let's see, which pin would that be? We want GP, so let's do the 0. So that would be the gamepad 0. Let's try to do this. This is very noisy, I know, because I don't have ground properly connected. So let's see, can I connect this to here somehow? I need better distribution of grounds. There we go. All right, so is that 0? I don't think this is 0. I think this might be 0. There we go. There we go. Very good. So this is gamepad data, as you see. I should have showed you that earlier, but that's basically how the data comes out. So we have the buttons that I'm pressing here. Let me just, let's not pull out the Ethernet cable the second time, but yeah, so I'm pressing the first button, second button, this is, this way. Second button, then we have third, fourth, and then up is fifth, and so on. So we could, these gamepads are horrible though. It's like I'm trying to press only the right button, and it's very easy to press it like askew. See, this is how you see if the gamepads are crap or not. But yeah, they're cheap. Anyways, so that's how the data comes out. Yeah, so that would be that part. And now I would like to show you the audio output. And so for that, let's go to the desktop again. We can get out of the terminal. And I think this should be one of these. I don't know which one of the Sublime Text windows. Up5 demos. So this is the gamepad. Oh, this is the audio. So essentially, the big difference. So in the schematic, if we look at this, the audio output are these two pins. So what we are doing, or what the theory is, we either can send out PWM, so pulse width modulation, where you have a signal that goes up for a certain time and down for a certain time, and the ratio between high and low is what the signal is. In our case though, we want to use something that has better characteristics, which is called PDM, which means you pulse division multiplex, or pulse density multiplex, sorry, pulse density multiplex, and a modulation, again, wrong term, pulse density modulation, that's the right term here. And so you have a accumulator that is accumulating the error of your signal. So if we look on Wikipedia or something for PDM, let's see, can I open the right window here? There we go. PDM modulation is quite a pulse density modulation. There we go. First order delta sigma. Yes, thank you. So essentially, if you have the signal is high, you have a lot of blips, and if it is low, you have a lot of zeros. So essentially, you accumulate, like, differentiate and integrate the error, and so based on if the error is above what your target is, you will send out a 0, and if it is below the target you want, you will send out a 1. So basically you are tugging a line up and down based on the error that you are calculating. So essentially you want, if you have a sanity check is 50% output requirement. If you have 50% that you want, then the bit will be constantly toggling on off, on off, on off, on off with the full frequency of your signal. So basically you tug the line high, you will overshoot the 50%, and then with 0 you will overshoot the other way and overshoot. So basically you will go up and down 50% time high, 50% low at the full frequency of your clock. So that's PDM. And this is what we wanted to do, but I wanted to do something nicer. So I wanted a sine wave to be generated. So what I did is here it's the module called Pdm Sine Mod, and this thing essentially takes I generate with C a sine table. So there is also a file in C that takes generating a sine lookup table from 0 to pi half. So essentially you are not creating the full sine wave, but you are generating values for 1/4 of the cycle, because everything else are very simple modifications. So the first quarter you can mirror, and then you get the second quarter, and then the third quarter you can take the first one and flip it just down, right? And then again mirror that. So you only have sign changes for top and down, and flips from for the horizontal. So horizontally you are flipping, and vertically you are sign changing. So what I did is take that sine table, which is 31-bit values, because the 32nd bit is the sine for the output, and for the input I have I think, yeah, there are 1024, so 10 bits input. So 10 bits input and 32 bits output for the full output. I think it is way too high resolution. I don't think we need that much, but that's what I did. And you're welcome to improve it and make it better. But yeah, this was good enough for testing. So so this is what this is a special block that takes the sine mod table. Oh yeah, so this is the test bench for this sine. For this is how I debugged it, and sine mod essentially creates a register with sine OBW, so sine OBW bit width, so it's 32 bits, so 31, so 0 to 32. Then I take the lookup table. I have so many values as I need, so 1024, or no, sorry, just 8 bits, so 256 values, and then I load it using initial read memh, which is a Verilog way of loading an external hex file. I load that hex file with the lookup table values, and then I have a combinatorial logic, which is probably a terrible idea, that takes that lookup table and converts it accordingly to output a 32-bit value by inputting a 10-bit value into it. So it takes the input bits and with the input bits it finds out if it should be sign inverted or not. And for sign inversion I take negate all the bits. It's just pure binary logic definition. So I'm sure this can be done better. Combinatorial logic, I'm sure this is pretty slow, but I bet someone that knows better ways of implementing digital logic will tell me how to do it right. But that worked good enough to actually generate the signals for me. And then I generated the sine counter. Sine counter is essentially an input where I tell how fast to advance the clock. So I have a counter that has like a fixed point math where I split it into two 10 bits. The higher order 10 bits are before the comma and after the comma in the digital in the number, and only the higher bits are necessary, so I can have fractional increments. So I have a fractional divider of the input clock. It's a little bit overcomplicated. I don't want to I could explain it in detail, but I think that's a little bit out of scope of today's stream. At least we can revisit it at some point. Anyway, so I generate a counter that essentially goes through the lookup table at a specific speed. So I want to generate a sine wave with a certain frequency, so I have to count through that lookup table at a certain speed based on the input clock that I have, the 42 megahertz input clock, which is the same one as on the other example. And so I race through that, take those values, and based on those values, I generate the PDM signal. So I take input clock, divide it down fractionally into a certain counter that goes through the lookup table, resulting in a specific sine frequency that then I'm converting into PDM, which is this result here. We can really quick run the simulation on this. To just take a look how the simulation looks like. So you see there is the Gen sine table. So this is how the hex values of the sine lookup table looks like. Basically make Gen... make not Gen, it's Pdm Sine Mod VCD. I can close the previous example. So this is our gamepad simulation. I might have it already open in here. There we go. It's already set up. Look, I prepared something. Anyways, this is from previous, from me testing this stuff, but this is a good example how it looks. So I also used, so this is the lookup table output, which is a signed value, and then I convert it to a level, which is not a signed value, so it is offset from 0. So it's from 0 to whatever, to all 31 bits. To 4,000 something. So you get the output values and then you generate the PDM. So you see it's high when it is high, and it's toggling less, and then going down for the result. So this is the internal state. If we can look in here to see the other signals. So we have clock, we have clock divider, we have a strobe. The important thing is, because I had to pipeline a thing here in the PDM, I have to have the clock divider to run. I have to have the divider to divide at least by 2. If I divide by less than 2, then the PDM will not work. Because I have this staggered, I have strobe at PDM strobe, which are basically pipelining the output from the PDM from the PDM generator. So if you look here, I have strobe and I copy the PDM level from the lookup table. So lut out and then save it into a register, the PDM level, and then only in the second step I take the PDM level and generate the delta sigma PDM output. So that's how you pipeline stuff. Essentially, that's how you speed up things that take longer. So you have something that will just either, if you do it combinatorial logic, it becomes just too long and it takes too long. So you split it apart and set it side by side. So in one clock cycle, you do one thing, save it, and then feed it into the second cycle. But because everything happens in parallel, this is actually constantly feeding each other. So you create, you trade delays or clock cycle time for speed. So you run faster, but you do less things in each cycle. So your clock efficiency is lower. But that's how you would do pipelining. That's a very different idea than, or not very different. It's not the same thing as pipelining in a CPU, although it is adjacent. You also have like a pipeline of steps that you are executing in a CPU. So it's the same idea, but then you have the invalidation of the pipelines and stuff. In this case, it never invalidates. It just streams through the system at a constant rate. So I hope I'm not misrepresenting it too much. It might be a little bit oversimplified. But yeah, that is an example of pipelining here. All right, so now that we have that example, now we can flash it onto our board. Let's program it. And there we go. So let's see. I don't need the gamepads now. All I need is, let's see, let me think. I think I only had the output of the, oh right, I had the input to the audio connected, which would be pin 1 here. Let's do left. Left would be here. There we go. So that's PDM output. And then we can connect the green one down there. That should be the output of our audio. So let's try to get a trigger menu and trigger it maybe on channel 4. And then level. Sorry, I'm covering it up. And then there we go. That's the audio. There you go. What doesn't look entirely right? I'm sure it is wrong. Sylvain, I am 100% sure it is wrong. I did my best to wrap my head around this. I might have done it. It's probably something I'm missing. But anyways, at least the output seems to be fine on the first glance. So we have the PDM input on top, and then we have the after the audio circuitry, which if we look at the design, we have audio R and audio L coming in, which would be the PDM signal. And this buffer inverter essentially acts as a two-pole RC filter, essentially, or it could be equivalent to a two-pole RC filter, but it has a sharper cut. So this is there to have a sharper cutoff for frequencies, but essentially it is a low pass. So it takes the high frequency PDM, filters it down to create an audio output that is then AC coupled to the audio jack. And now let's see if we can get that on stream. So let's cover your ears because it might be loud. The sine wave will be distorted, but let's see. I did get a USB to audio converter. So let's see if we can get that to work. Stereo capture. Let's turn it down. Sorry if it was loud. Is that hearable? Do you guys hear the beep? Because I'm not sure I have it on the monitor. So it should be a sine wave beep that you hear. Can you confirm that you hear it? Yep, okay. So yeah, that is the output of this. Oh. Doesn't sound right, does it? It comes with a... That is not a sine wave. That's definitely not a sine wave. Okay. For some reason, it has a very long delay to come out on my monitor. So that I don't know exactly why that is. It was supposed to be a sine wave. Oh, probably it is saturating. Yes, way too high amplitude. So I probably have to decrease the amplitude. Much too high amplitude, yeah. So let's see, can we really quickly do something to decrease the amplitude. Is this wrong? Maybe I should just... yeah, it's clipping. I should probably just shift it. Just use less bits, right? Because... But then it has to be still centered. So how I should shift it in the sine counter, LUT in. So probably I should do it when it's still... how do I do this? Because the dividing is, I should basically use some shift, but I have to shift it before I put it into the LUT, I think, because the yeah. Let's do yeah, so Sylvain has a solution. LUT out should be essentially bit width 1, bit width 2. So, oh yeah, so LUT in. Sino bit width. I'm just trying to figure out what you're doing here. In the PDM code? Oh. In the PDM code, LUT out, and convert that to... Oh, convert that to this. So take this. Let's see. So you say like this. Should I do this? Is that correct? Yeah, that sounds about right. Okay. Yeah, let's try that. See what happens. So yeah, let's rebuild. This takes actually a while to synthesize because I was too lazy and I didn't actually do it so that the lookup table is stored in block RAM, I think. Yeah, there's no RAM being instantiated. So this is something I should do at some point. Is instead of wasting a lot of logic in the chip for the lookup table, it should be in the RAM instead, but I didn't do that. So let's see. So yeah, the amplitude is definitely lower if we look at this. There we go. That looks good. So let's see. Let's plug this in again. Yeah, it seems to have like a lengthy delay for me. Yeah, there we go. Yeah. How does this sound? You guys hear it before I do, because I have a really long, like 30-second or something delay before I hear this stuff. Sound same? Yeah, well. Okay. Anyways, we can keep working on this. I think on stream, yeah, it still sounds terrible. Now I hear it. Now it finally came in. Okay, leave, stop, please. It's horrible. Okay. Okay, now it stopped. Okay, cool. Anyways, it's not perfect, but at least on the oscilloscope it seems to be doing the right thing. I don't know why. Maybe it's all possible. We will not be debugging it now. I refuse to debug it on stream. Especially it's like yeah, we can play with this at some point. Maybe we can even do it on stream at some point and like actually debug it into detail. But for now, I would like to move on because first of all, we are already over time. And second of all, I wanted to show you one more really cool thing. That this Pmod was originally made for. So the original inspiration was not ScumVM, which came later, which is I'm really looking forward to. But the original inspiration was NES, actually being able to play NES games on the Icebreaker. So let me disconnect this because we don't need that anymore. But what we do need, let's not disconnect the Ethernet. That's the important part. So this one can switch off. There we go. And zoom out. Rising, thank you very much for the follow. Welcome to the stream. Okay, so let's hook it up. Let's see if we can get it to work, because the longest time, what took the longest actually was figuring out how to program the design correctly. So if we look here, this is a module that implements NES. So there is a DMA controller, but essentially memory multiplex. So this is an NES. So it consists of much more Verilog. There is a much more separate block. So you have pixel processing unit, PPU. There is the PLL to get the clock. Then memory management unit, MMU. The microcode is in here. And there is a lot of different modules that come together to implement an NES. It's not perfect, but I would like to see if we can. It is a DVI and difficult to make sound work. And yes, so you can't do that unless you sign. I wanted to mention that in the very beginning, but I got distracted. We are using a DVI chip because you don't need to sign an NDA for it. If you are using anything that has anything to do with HDMI, you have to sign an NDA because of HDCP, so DRM related garbage. This is incredibly infuriating that you can't buy, as far as I know, HDMI encoder or decoder chips without signing an NDA. You have them listed on DigiKey and Arrow and whatnot, and they are considered not in stock. Contact us because you need to sign an NDA so you can work with those chips. And you need an HDMI encoder chip in configuration like this, at least. It's like, unless you have an FPGA that is directly generating HDMI, that's the advantage of the ULX. It can generate the signal with audio built in, because it generates it inside the FPGA. But you can't, as far as I know, generate 1080p, correct me if I'm wrong, with an encoder chip. This is the architecture. Like, look at this. I have this HDMI capture devices. I will have to disconnect it anyway, so let's do that. So if you look at this, so this is my Magewell. I think that might be visible. So this is my Magewell. This is an HDMI to USB converter. Inside this thing can only do 1080p 30 or 7020 60, not higher. Okay, now that's correct. Okay, so you cannot do 1080p 60, for example, or stuff like that. So can do VGA at most without encoder. Correct. So for the ICE40 we need an encoder because we need to be able to do any DVI related stuff. With the ECP5 you can do a bunch of the HDMI stuff, including audio, without the HDCP garbage, and then send that out. And here the Magewell, for example, is an ECP5 inside. I have even photos that I posted to our chat with an analog devices decoder chip. So it is able to go to 2K, this particular part. They also make a capture device that's also an ECP5 with a faster decoder, I think, that can do 4K. So you can go to full 4K resolution, probably with the ECP5 too. I might be overstating it, but it might be possible with an encoder chip. I would have to do the math, but the encoder chips are very useful. I wish we could use them and just buy the chips. I am somewhat inclined into signing an NDA to build a device using the encoder chips for HDMI and get the audio, but I have too many projects already, so I'm not sure that will ever happen. All right, anyways, so for open source, if you have to sign an NDA and you cannot like share maybe even the designs, I don't even know. You can't even buy the parts as a normal person without an NDA, so it's not really helpful as an open source design. So that's why I'm not doing it for this. Okay, so let's go back to the this. It was pressing on my buttons, and what we need to do, I can put this away, and what I wanted to try is to get this to go up 5K demos. So great thanks to Laurie, who ported Dave Shah's port of the course from what is it called? Also an FPGA retro gaming emulation hardware. So it's like people standing on the shoulders of shoulders of shoulders. So this is like a really huge collaboration thing. It still needs some work, but let's take a look at this. So so I have Micromage's NES design in here, you see. There it is. And then there is a Python script that can convert the Micromages into a bin file. This is what we are storing after our bitstream as our cartridge. And so I think this should be still stored in there. So if we program this, so that should do the HDMI stuff. And now, if we go in our microscope view, this is there we go, Micromages. Isn't that awesome? And this is running on the Icebreaker. So we have NES running on here. And this is meant, basically this guy is meant to plug in where the head is of the Icebreaker, and we can display it. The cool thing about, so I'm doing it with the Magewell because this is as far as I know, I have also an Elgato HDMI converter. I really recommend the Magewells, despite them being more expensive. They're really worth just for the software they have. So if I do, there is a USB capture utility, which I would like to show you. And so first of all, this is how it's hooked up over HDMI to the Magewell, over USB to the computer. And this is the software. So you see here this is actually showing you stats of the HDMI signal. The other thing that it does, it also has additional configuration of conversion. So the cool thing which Elgato doesn't have, you can add your own resolutions to the output. So if I have an input which also shows me what resolution, what frequency of the pixels, what the overscan area is, what color format it is, it also shows me much more detail. So see, mode is DVI, so that means no, that's exactly what we did here. That's why this Pmod is designed with taking gamepads and having the audio out, because we can't do it on the HDMI. That's why with this you get gamepads and audio, so you have a full-fledged game console with 4 controllers and audio output and HDMI out in one. So that's the point of this whole exercise, to convert an Icebreaker into either a Game Boy emulation, which there's also a port of that I didn't try out yet, or an NES. And this is what I'm so excited about. For the next stream, hopefully, or like if you follow me on Twitter, you will see if me to get this all connected, and then we can just show off that this works, and then we can make the next revision of this board with the few fixes. We have to definitely look into the audio part, but let me finish just showing off really quick the Magewell software. But it shows information about the details about the signal that is coming in, if it detects one, of course. And the other thing that I really like is, besides being able to edit the edit, so you can force a target device to whatever mode you want, there are also, you can add your own resolutions. So if we switch here to microscope view, I can switch it to 512/480 by going into here, I think, and then switching it to... Did it switch even? You don't even see it. Anyway, so you can actually get the native video out at the native resolution, and it can do upscaling for you. So the Magewell will do upscaling from that resolution, which you can add to whatever you want. And also frame rates are also supported. So you have multiple frame rates that you can list. Oh, sorry. You can configure and load. And also what I really like, if you have more than one Magewell connected, you can give them their unique names so that it is easy to find in OBS. So really, this thing is really making streaming and configuration and setup easier than the Elgato that are cheaper. And essentially it doesn't come down, the hardware is pretty much the same. It comes down to the software. I think the big problem was you could not just copy this bitstream to the Elgato to get a cheap version of the Magewell, because it's using a different encoder or decoder chip, so you can't just directly use it. But anyways, I really like Magewell. I use now both Elgato and Magewell is working pretty well. It still crashes from time to time, but this is, I think, more of a video for Linux issue than anything else, and USB in general being janky. But this works really well, and I'm looking forward to play some NES games on this. So yeah, I think we are at the end here. We have working games on this. I can even, let's repower this. Oh, maybe it reset even. Let's see. I think it reset 1080p. Okay. Oh, the video did reset. Weird. Okay, whatever. Doesn't matter. It definitely worked. The stars were sparkling. Yeah. I hope you enjoyed this. I tried to cover as much about the process as I could. This not surprisingly, everything takes longer than one expects. So last time we assembled the hardware, I wanted to have the designs to testing the hardware ready before the stream. Which was pretty silly expectation to have. So it took me another 3 days, 2 of them definitely full-time working on the design for the HDL. I do not consider myself a pro at a Verilog at all. I had to remember a bunch of stuff that I barely knew in the first place. So I should spend more time writing more Verilog. So don't see this. I hope this encourages you to actually try writing some Verilog or Nmeigen. I was hoping that I could show off today not only the Verilog implementation but also the Nmeigen implementation of this. But obviously I ran out of time. Maybe use it as an inspiration for yourself to implement these things yourself. You can get those gamepads really for cheap on eBay or something. They are not very good for actual playing, but they are definitely good enough for testing. And because they cost so little, you can just cut off the cable. MIPI DSI HDMI bridges. MIPI DSI HDMI. So I think this is a good question because MIPI DSI requires its own license to get all the specs. I think you don't get the specs of MIPI without signing some NDAs. Then HDMI itself is also requiring NDAs because of the stupid HDCP stuff that should be illegal in my opinion. And you wouldn't get audio because it's the current state of the world, unfortunately, with content protection, which I understand why people are doing it. And they want to protect their IP, but it is causing a lot of headache in other realms, and I'm not sure it is the price worth paying. Yes, there is. Yeah, but you need an NDA to use this chip. So you can't buy this chip from. I looked this ADV 7533. Did you find it? You can just buy it. I think they were colas only on the stores I looked at. If not, you can just buy them, that would be great. They have SPDIF and I2S sideband input. That would be, the datasheet of them is available. You can look at the datasheet. Yes, exactly. The quote button means that they will not give you a quote unless you sign an NDA. So yeah, that's the situation. I would love to play with those chips and build something with it, but it probably won't be open hardware. And it might still be worth it, and it might still be interesting if we keep all the other parts of the system open and actually make it programmable. And but I think Dave Shah made a correct call that I should be working on other things than this. Yeah, I got really nerd snapped with all the game console and retro computing recreational and archivist stuff, but yeah, maybe. Yeah, so there might be some solutions to this. I would love to get audio over HDMI, but it's not a really big deal because you can get the analog audio out, and most TVs have analog audio inputs, so you can hook it up, at least for DIY NES game console type of stuff. So that still might work. So build your NES console with your icebreaker. That's the call. And we still have some timing issues, I think, on the NES core that might need addressing, but it definitely is worth taking a look into it. There's some stuff that needs to be cleaned up. There's some makefile shenanigans happening that I probably will just push into my fork. So if you want to find the design that I forked from a fork from a fork, you can find it here. So up5k demos, I will paste it to the chat. So this is where the NES HDMI design is. So that's that. Then the second thing, because I really love that game. So one very exciting thing about NES, people are writing new, like brand new games for that console. So it really is a vibrant community. I really find it super exciting. If you are into games like Shenzhen.io, I recommend you try actually writing something for the NES, because it is also assembly, and you can, it's a 6502, it's really well documented. People put a huge amount of effort in documenting every single bit and quirk of that console. It's pretty simple because it's very simple system. So writing games for that is really really approachable. So if you want to write assembly and have a cool game to play, try installing an emulator with a debugger. There are emulators with debuggers. A good streamer to follow on Twitch is Zorkenheimer, I think. I call him Zork. Anyways, Twitch. Yes, that's him. Follow him on Twitch. He writes games for NES. He might be even online already, and if he is, we will definitely be raiding him. So this is his stream. Take him as inspiration. And Wednesday, Friday, and Sunday. So he will be streaming tomorrow, as far as I know. So definitely follow him. He's also very funny. Yeah, there you go. Good job, guys. And then Micromages is the game that I was playing, and it is a new game. There is a very good video where they describe how parts of the optimization they did to squeeze it into 4K kilobytes. Into 40 kilobytes. It's a 40 kilobyte game. 40 kilobytes of data. That's it. It's really cool, and it's a very pretty game. It's really worth it. You should buy it. You can play. If you buy the game from them, you can buy it on Steam, and the Steam game comes with the ROM that you can play in an emulator too. So you can buy it from them and have a new game for your NES, and that's something I would like to give you a shout out to. So Morphcat makes NES games, as far as I know. This is not their only NES game. So let me paste that in here too. And I hope we will be playing this. There is also a bunch of homebrew that are free, but there are also paid games that are more polished, and people put a lot of effort into it. So worth taking a look at. Oh, I was not showing you even the desktop. So yeah, that's Micromages, and that's the up5 demos stuff. Yeah. Anyways, I think that would be a wrap for today. As I said, we have one more revision of the hardware to make, and we definitely have to debug the audio and figure out if it is actually fully working the way it is supposed to. And then we definitely the pull-up resistors for the data lines, that it is something we want to add for a new revision. And then I think we can make a small batch if you're interested. I think in case of this, I will... no, it doesn't sound very good. It sounds better than on stream. It sounds more like a sine wave with the headphones. But yeah, I am not convinced that we are doing things right yet. It looks right on the oscilloscope, but maybe we are loading it too much, and so that's the cause of the problem. That our drive strength is not good enough, and we need an amplifier. That would be a way out if we are capturing it with the USB device. This shouldn't actually put much load onto the output, unlike the headphones. So yeah, anyways, we have some stuff to do with the audio stuff, but otherwise, again, thank you everyone for being here. I hope you learned something and you enjoyed yourself. I will probably make a list of people interested in those gamepad sets when we figure out the audio issues. I don't think I will be just making them and putting them in the store. This seems a little bit too niche for that, but I might take some small batch of pre-orders and put them together for the few people that might want a set like this, and then go from there. So that would be regarding this. Otherwise, again, as always, thank you very much for everyone who is supporting these streams. Thank you. Check out 1-Bit Squared for your icebreaker needs and other debug hardware. The list of tools that I'm using for the streams was updated. I moved it to my blog. So the link below the video is now directing you to my blog, where I put together a bunch of the tools that I'm using and a list, and it has Amazon affiliate links. It's like, I'm not a huge fan of Amazon, but this is a simple way of supporting this if you need some hardware anyways. Otherwise, again, thank you very much for everyone who is subscribing to this stream. This really helps. I really appreciate it. And Icebreaker upgrade kit, yes, I will do that. Thank you for reminding me. So for the SRAM and the RGB LED and whatnot, that's definitely on the to-do list. There's a lot of things that are on my to-do list, like the HyperRAM Pmods need to go in stock. I ran out of Blackmagic probes out of stock. I'm producing them now. It's just too many moving parts. And I have also had to take on a consulting job because of how things are working out. So if you want me to keep doing this and you have some spare money, if you don't worry about it. I really appreciate you being here. The motivation of having people and being able to share this with people is all really worth it. But if you want to financially also support this, and you think this deserves it, which I hope it does, check out also Patreon below. And again, I would like to, so one thing I definitely need to do before we go. This time I have only my monitor on, so I was checking that. Yeah, let's see. I have to do this really quick, because the list that I have hanging here is not up to date anymore, because some wonderful people joined the support here. There we go. I think I'm almost there. I wish this computer was a little bit faster. Come on, you can do it. There, come on. There we go. So yeah, I would like to say big thank you to those supporters that in the shoutout tier and beyond. Thank you very much to Jamin, Brennan Ashton, Drew Fustini, Edward Borden, Go Jimmy Pie, Jeff Wang, Jordi Parky Rodriguez, Kelly, Miha Benovets, Sid Price, Tom Keddy, and since last week also to Sean C. Thank you so much, and Matthias Pritchett. Thank you very much for your support. I really appreciate it. It really helps with the expenses and the hardware. It's like making all these prototypes and creating content for this is not free. But I appreciate you all for being here. This community is wonderful. Love you all. And as always, if you have been, thank you for watching. Bye.